Hi, thank you for tuning to my presentation today. I'll be talking about some initial results of localized waveform inversion with multiple seismic observable, including translation, rotation, and strain. My name is Shihao Yuan, and this work was done with my collaborators Heine Eagle and Joachim Wassermann at the University of Munich. In oil and gas industries, 4D seismic aims at retrieving small temporal changes due to fluid injection and extraction. To capture those small structural variations, we tend to use more quantitative and high-resolution techniques such as waveform inversions. The waveform-based algorithm can be computationally very expensive, mostly due to the large size of the discretized model. In fact, during time-lapse surveys, our target areas is normally much smaller compared to the full background models. Therefore, performing waveform inversion only within the target areas can be particularly useful for the numerical cost reduction. For this purpose, we can combine the wavefield injection method, which allows us to restrict wavefield propagation modeling into a subvolume and thus avoids repeated simulation in external non-target area. This method can be applied to most numerical schemes, such as finite difference and finite element method. In general, each source location requires one full simulation of the entire model, during which we will store the wavefield along the so-called injection boundaries, enclosing our target region. Following these pre-calculations, the stored wavefield for each source will be treated as the new boundary conditions for subsequent local simulations. Local simulation techniques are mostly model-driven approaches, which means a precise modeling highly relies on an accurate known background models. This assumption may be challenging in case of unknown perturbations and background model errors. However, if there are some observables that are kind of short-sighted, in other words, their sensitivities are only limited to the target areas, that will make the local solvers more robust and the localized inversion scheme both efficient and accurate. Speaking of seismic observables, most seismological observations during the past centuries were carried out with seismometers, which mainly record translational ground motions. However, ground shaking caused by earthquakes, landslides, volcanoes, and any other natural or anthropogenic sources will not only generate translational motions, but also rotation and strain motions. In recent years, with the availability of new seismic instruments, such as rotational sensors and distributed acoustic sensing, more complete ground motions can be recorded. These new observables essentially represent the spatial gradient wavefield, which are expected to be more sensitive to local structures at the measuring point. This has been verified in Singh et al. 2019 with 2D examples. They inserted a velocity perturbation with a checkboard pattern into a constant background models. Particle velocity, strain, and rotational components are simultaneously recorded at 4 points represented by the numbers across the edge of the perturbations. Their waveforms under the background and perturbed models are then compared with each other. As is shown in the right panels, strain and rotation components present much more evident difference in two models, implying that gradient wavefield is indeed more sensitive to local small-scale structures than particle velocity. However, that is not our ultimate goal. If we can somehow combine the translational and gradient measurements, in other words, enhancing the local small-scale sensitivities while reducing the source and traveling effects that are far away from the measuring point, that would be the best for the proposed localized inversion scheme. Almost a decade ago, even before the emergence of commercial rotational sensor and distributed acoustic sensing for seismic applications, Fisher and Eagle 2009 did some inspiring work on analyzing multiple seismic observables. It has been shown that ratio-based observables have some desirable characteristics. To be more specific, The root mean square amplitude ratio between velocity and rotation is called apparent s-wave velocities, beta. Similarly, the apparent p-wave velocity can be defined with the velocity and strain components. To avoid division by zero, a time window for each individual quantity has to be applied. The relatively sensitivity density of both combined observables can be expressed as a differential sensitivity of translational and gradient wavefield alone. Let's take the apparent s-wave velocity as an example. Assuming relay waves propagate between the source and the receivers, as shown in the figure, the difference of the sensitivity between the velocity and rotation is primarily concentrated beneath the receivers. Now it seems that we find a suitable observable that may satisfy the localized inversion scheme. The sensitivity kernel shown in previous figures represent the first derivatives of the select observables with respect to the s-wave velocities. In other words, it describes changes in response to an infinitesimal s-wave perturbations. To further demonstrate the near receiver sensitivity of the newly defined observable in case of finite variation of velocity structures, we can perform a simple perturbation test. This time, we focus on the apparent p-wave observables. Two square p-wave velocity perturbations are added on the right side of the single source, and an array of receivers are put on the regular grid points. In the first simulations, we compute synthetic velocity, strain, and apparent p-wave velocities for the background models. These provide reference amplitude values for each observables. We then perform another simulation under the perturbed models to calculate the relative amplitude changes at each receivers. For velocity, the relative amplitude changes are more averagely distributed along the traveling paths. Strain measurement show a similar pattern, but with sharper boundary of the perturbations. For the ratio-based apparent p-wave velocities, the propagation effect has been mostly removed, and the pattern of relative amplitude changes agree well with the true velocity perturbations. In general, the finite response of each observable is consistent with the sensitive kernel shown before. Now we can move on to localized inversion with these newly defined observables. We first tested in a 2D medium with linear increasing velocities. The full background model is 4 by 4 kilometers, and the target models, denoted by the dashed square, is 2 by 1.4 kilometers. We use 7 sources and a Ricker wavelet with a 4.5 Hz center frequency as the source time functions. Certain receivers are put into the target areas, and a s-wave perturbation of minus 150 meters per second is added beneath the receivers. We record both particle velocity as an apparent s-wave velocities as our observables. To perform localized inversions, we store wavefield along the dashed square beforehand under the known background model so that we can apply the wavefield injection method to efficiently simulate local wave propagations within the targeted regions. We choose the classic L2 norm misfit functions to iteratively minimize the difference between unmodeled and observed data. After 10 iterations, the true perturbations and the inversion results are shown in figure A, B, and C. The corresponding 1D profiles along the white dashed line are shown in figure D. First, the inverting maximum perturbations from apparent s-wave velocity measurement is more accurate than that from translational velocities after the same iteration. Second, the resolving power of the new observable is also higher than the velocity component. This can be attributed to the more concentrated sensitivity of the combined observables. In the second experiment, we keep the same model size and acquisition geometries. Besides the real perturbation within the dashed squares, we add 3 unknown S-wave perturbation indicated by the arrows. These unknown perturbations do not exist during the first full model simulation. That is to say, the stored boundary wavefield and the subsequent local simulations may be inaccurate. Apart from that, those unknown perturbations during the localized inversion can't be corrected, since the model updates are merely allowed within the target region. Now let's check how our localized inversion behaves during different seismic observables. This figure shows the true and inverted perturbations starting from inaccurate background models. The inverted structural anomaly from a velocity component is slightly shifted upwards and mixed with some artifacts, while that from apparent S-wave velocities remain nearly as accurate as before. 1D profile shown in Figure D gives a more clear comparison of the inversion results using translational and combined measurements. Given above facts, we may say that apparent S-wave observables are basically unaffected by some model inaccuracy that are not in the vicinity of our target areas. In the four examples, we simply want to test the same idea with more complex background models. We still use the same acquisition geometry, but modified Mamouzi model as our background models. We add the same shape and the same amount of S-wave anomaly within the area of interest to mimic the potential time-lapse perturbations. The localized inversion strategy stayed the same. The results are shown here. Like the first experiment, the velocity anomaly can be achieved from either translational or combined observables. However, inverting apparent S-wave velocities will lead to a faster convergence and higher resolution. In summary, this study has shown the possibilities of applying some new observables such as apparent P and S-wave velocities to localized waveform inversion. The near receiver sensitivities of the amplitude ratio-based observables has made model-driven local simulation approaches more robust and resistant to background model errors. It is as if we are viewing local areas with a magnifier and neglecting what happens outside. In fact, this concept is not limited to time-lapse service in exploration seismology. It also applies to large-scale structure inversion with multi-type waveforms. The combined observable used in these studies enables seismic tomography without travel times. Due to this fact, the influence of traveling paths and inaccurate source time function or positions can be mostly mitigated. If you have comments and questions, you can contact me through the following email. Thank you for watching the talk. I also want to thank my collaborators and the session conveners. I look forward to seeing you in the live session on Monday, December 13th.